Let me introduce Olaf Kindring. I'm excited to present on the 8 multi-core RISC Vs in a very low-cost $38 FPGA board. So you're standing between us and lunch. Good luck.
Hi, I'm Olaf Kindring. I'm a senior digital design engineer working for Camcom. I am also a co-founder and director of the Fosse Foundation, creator of the award-winning FuseOC package manager, father of 2 not very award-winning kids. I'm a viral tweeter, but the reason why I'm here today is to talk about my bit serial CPU, which is an award-winning CPU from the RISC V soft CPU contest last year. And I would like to extend my thanks to the RISC V Foundation for this contest. Me and my girlfriend has been saving up money to buy an ARM license for a long time, so the money will come in handy. So what's a bit serial CPU? Okay, let's do a simple example here. We have, in this case, an 8-bit processor. We do an OR operation, you need 8 OR gates. If you have a 32-bit, you need 32 OR gates. Let's just keep one of them. And instead, we slide the source and destinations through this OR gate, and we can trade speed for area, or the other way around. That's how we see it. So this will take 32 cycles to complete a single instruction, but instead it will just use 1 gate. So it's really a very small design. Same thing if we look at the add operation. Here you need to save a carry bit between each iteration, but it's the same principle. You go from the LSB to the MSB, and most operations work very good in this way. So the CPU itself, it's a RV32i, which is the base specification. It's been firmly verified with RISC V formal. It's tested in hardware on the tiny FPGA BX, which is this $38 FPGA board I'm talking about. I'm packaging for FuseOC, which I will talk about more later today. And it's BSD license, or actually it's ISC license, but it's kind of the same thing. So it contains just enough of the privilege spec to run the compliance test and run Zephyr OS. How fast is it? Most instructions, as I said, take 32 cycles plus some overhead for memory. Some instructions you need to take 2 rounds. Jumps, for example, you need to check if it's misaligned before you decide if you jump or not. There's probably ways to optimize that. I'm not an academic, so I don't know. Same with load and store instructions. One annoying thing is the set flag instruction, because it sets the LSB, but when I have calculated if I need to update or set or not set the bit, we have already passed through that, so I need to take the instruction 1 more round. Shifts, yeah, dependent on number of shifts. It's semi-fast. It's not super fast, it's not super slow in terms of raw CPU power. So I would like to tell you about how small it is, but before we can do that, we need to have some naming conventions. So serve is the CPU itself. And if we put a serve together with some GPIO, timer, some memory, we have a servant. And this is enough to run Zephyr OS. If we then take this and add some clock generation stuff, we have a service for the RISC-V. Or we can do it for Cyclone 4E, which is the case it's become a survive. Or an R67, in which case it becomes a cervix. And if, at some point, someone wants to send this to space with the European Space Agency, we have a Cerveta. It hasn't happened yet, but I don't know, maybe. So now we can talk a bit about, oh yeah, sorry. So we can put several servants, and we have several of them, Holo servants. So how small is, yeah, I did some calculations or some synthesis experiments with Yosys for Xilinx-based devices, Intel-based devices, and lattice-based devices. I didn't do a gate count. Someone can probably help me with that. But you can see it's about 350 registers. The number of LUTs depends on the LUT size, and in the Xilinx case, it's managed to use probably distributed RAM instead of using one of these block RAMs, which is optimization. 10 of them, these servants, fit into the smaller board. And you have a $1 per servant count here. Also, we're running it quickly out of I/O when we have 210 cores, if we don't do some clever stuff. But can we do better? Yes, we can. We can remove the timer. Now it won't be able to run Zephyr, of course. We can move out the memory. And then we can put several of these servettes with shared memory, because as you saw, these are memory constrained in most FPGA devices, at least the ones I tried. 16 would probably be the best for saturating memory, since you need 2 cycles basically for memory operations, and every instruction is 32 cycles, so yeah, it probably saturates the memory quite nicely. 2 is probably the best trade-off between logic and memory usage. So I did that, and it turns out my title is very out of date, and I'm able to fit 16 of these cores. This is without the timer and stuff, so you won't be able to run Zephyr, but you can, I don't know, blink LEDs or something. You don't get that much memory for each of them. Oh, this was also dubbed Jingluns Law now, that every month you get an increasing number of CPU cores on your FPGA. So what can you do it for? Well, you can actually have this for real things. You can use it for CPUs where you don't need any processing power. You just need a small glorified state machine, power management, or DRAM initialization, where you can, which is quite nice. Control plane CPUs if you don't have a fast control plane. And if you put many of them, you can run sensor hubs where you perhaps collect data from a lot of different sensors and just aggregate them. And these embarrassingly parallel tasks that were all the hype a few years ago. But there's more to be done. I don't really have that much time to spend on this. Just throwing it out there in case someone helps. It's open source, you can help out. So one thing is to share the code and the registry file in one RAM, because the block RAMs in FPGAs are much larger than the registry file, so a lot of these areas just goes unused. We need to put that to good use. There's a lot of optimizations that can be done on different levels to optimize for different LUT sizes and things like that. LUT golfing is a fun word, I think. It's the process of trying to figure out how few LUTs you can use for a specific task. Now, of course, implementing the C extension would make a lot of sense, because it's a small core, but it's not very useful if you need a large memory. So that's something I would like to do also, to make it run from Flash and UART bootloader. These are outside of the core, but part of the package. And that's it. Thank you.